Welcome to podcast number 5, where we're going to look at the calculations of polyprotic weak acids and how those factor into our weak acid equilibria calculations as well. Well, when we're talking about polyprotic weak acids, right, those are acids that have multiple ionization steps. So there are multiple H's out in front that we can use in subsequent steps. So in the first step, you're going to give off one proton, and then whatever you're left over with is going to then be allowed to give off another proton, and so on over successive steps. All right, and so what we find is that the equilibrium constant, right, is becoming smaller and smaller with each step, meaning that Ka for step 1 is going to be greater than Ka for step 2, and so on as we go through these. Let's take a look at our phosphoric acid as an example of a polyprotic acid here. And notice that, right, our phosphoric acid, H3PO4, is going to give off one proton and become H2PO4. And then in the subsequent step, now that H2PO4 can then give off another proton and then become HPO4 2 minus. That could then give off a third proton, finally becoming PO4 3 minus. And so notice that each one of those has an equilibria constant that's associated with them. And as we talked about, right, they become successively smaller, or the acids become successively weaker, right, as they are progressively giving off more and more protons. It's harder to remove an extra hydrogen. Okay, so let's then see a sample problem working with polyprotic acids and what we need to do with them. Well, here we have vitamin C, and vitamin C happens to be a diprotic acid, and we are given two different Ka values. It wants to know what is the pH of a 0.63 molar solution of our vitamin C. So first off, let's assume that the only acid is going to come from the first dissociation, right? So this reaction is where all of the H plus is coming from, not the second successive step. We'll see what happens in that step in a little bit. All right, so if that were the case, then I could say Ka1 is equal to, right, H plus times HC6H6O6 minus divided by, all right, our H2C6H6O6. All right, and if I plugged in some values here, I would say that, all right, Ka1 is 7.9 times 10 to the minus 5th. And that's going to be equal to, all right, well, we're going to have x squared on top divided by our 0.63 molar to begin with minus however much of that goes away. We want to say, can we ignore this? Meaning, does it ionize less than 5%? That'll make this a non-quadratic to solve for. So let's see on the next slide if we can do that. So remember, one of the ways that we can determine if we can ignore that is by doing the Ka divided by our initial concentration of Hb. Well, we knew both pieces of information of that, and so when we solve that, it's 1.3 times 10 to the minus 4th, which does happen to be smaller than 2.5 times 10 to the minus 3rd, so we can ignore that bottom x, which then simplifies this problem, right? Because we can get rid of that, and so now we know that this is going to be 7.9 times 10 to the minus 5th is equal to x squared over 0.63. That's a heck of a lot easier to solve than a quadratic is, and we can solve that our x is 7.1 times 10 to the minus 3rd. All right, remember that x was equal to our H plus concentration. And so we can solve for our pH is the negative log of 7.1 times 10 to the minus third, which is going to be 2.15. All right, so we assumed that all of our acidic character came from that first ionization. Now, what happens if we add in a Ka2, right? How does that affect things? Is that going to affect our overall pH? And if so, then what's the calculation that we have to do? So let's see that on our next slide. So adding in a Ka2 becomes a little bit more complicated, which is why I've written out GR here, is because it's going to be a little bit more work. First off, we have to think about what that second reaction was. So the second reaction was, we have now our C6, or our H, C6H6O6 minus is going to then come to equilibria with another H plus. I'll put in the phases just to remind myself here, and now we have C6H6O6 2 minus. All right, now let's think about then a new ice table for this. So I've got a new ice table now for the successive one. All right, now, initially, how much of this weak acid do we have? Well, we have as much as we produced from the first ionization. So whatever we solve for X in our first ionization, that is what we are starting with here. All right, well, X was also equal to H plus. So we're not starting with none of it this time. We're starting with a little bit of it, 7.1 times 10 to the minus third. All right, but we have not yet made any of the C6H6O6 2 minus. We haven't made any of that yet. We didn't make any of that in step 1. All right, now, how much are they going to change by? Well, we aren't 100% sure, so we're going to say that this is going to go down by X, and our products are going to go up by X. So 7.1 times 10 to the minus third minus X, and we have X and X. All right, so now, right, if I want to solve for Ka2, all right, well, Ka2 is given to us as 1.6 times 10 to the minus 12th. All right, that is equal to, all right, so, oops, and this should be 7.1 times 10 to the minus third plus X. Oops, I forgot that. Okay, so it's going to be our H plus, which is 7.1 times 10 to the minus third plus X times X divided by 7.1 times 10 to the minus third minus X. All right, now I'm going to rearrange some stuff here, and I'm going to move the denominator over to the left-hand side there. So I'm going to end up with, I have 1.136 times 10 to the minus 14th minus 1.6 times 10 to the minus 12th X is equal to 7.1 times 10 to the minus third X plus X squared. All right, so we're going to continue to do some algebra here. I'm going to get the X squared plus 7.1 times 10 to the minus third minus 1.136 times 10 to the minus 14th is equal to 0. So this is a quadratic no matter how we want to do this. That should be an X in there. Sorry. And so we find our quadratic. I get X is equal to 1.6 times 10 to the minus 12th. All right, so if I want to find the pH of this, that is the H plus concentration. So the pH is equal to the negative log of H plus All right, so that's the negative log, and our H plus in this case is 7.1 times 10 to the minus third, plus our new X, 1.6 times 10 to the minus 12th, and I get 2.15, same answer. So there's no reason to go through and do this Ka2 or the Ka3. They're so small in relation to Ka1 that they are not going to make our solutions any more acidic based on their pH. Yes, they are by a very, very tiny amount, but not enough that we're going to see in our answers. So don't worry about going through and doing those. If you have a polyprotic, just worry about Ka1 and be done with it. All right, so that ends polyprotic acid. Next, we're going to turn our attention to weak bases, which are going to be solved very similarly to our weak acids.